In this section and the next few lessons, we're going to talk about dimensionality reduction. The number of input variables or features for a dataset is referred to as dimensionality. Dimensionality reduction refers to techniques that reduce the number of input variables in a dataset. More input variables often make predictive modeling tasks more challenging to model, more generally referred to as the curse of dimensionality. High dimensionality statistics and dimensionality reduction techniques are often used for data visualization. Nevertheless, these techniques can be used and applied to machine learning to simplify a classification or regression dataset in order to better fit a predictive modeling problem. The performance of machine learning models can degrade with too many input variables. If your data is represented using rows and columns, such as a spreadsheet, then the input variables are the columns that are fed to the input to the model to predict a target variable. These input variables are also called features. You can consider the columns of data representing dimensions of an n-dimensional feature space, and the rows of your data as the points in that space. This is a useful geometric interpretation of a data set. Having a large number of dimensions in a feature space can mean the volume of that space is very large, and in turn, the points that we have in the space, the rows of data, often represent a small non-representative sample. This can dramatically impact the performance of a machine learning model fit on the data with too many input features, generally referred to as the curse of dimensionality. Therefore, it's often desirable to reduce the number of input features. This reduces the number of dimensions of the feature space, hence the term dimensionality reduction. There are many techniques that can be used for dimensionality reduction. In this lesson, in this section, let's review a few main techniques. Perhaps the most common are the so-called feature selection techniques that use scoring or statistical methods to select which features to keep and which features to delete. Two main classes of feature selection techniques include wrapper methods and filter methods. Wrapper methods, as the name suggests, wraps a machine learning model, fitting and evaluating the model with different subsets of input features, and then selecting the subset of features with the best model performance. RFE is an example of a wrapper feature selection method. Filter methods use scoring methods, like correlation between the features in the target variable, to select a subset of input features that are the most predictive. Examples include Pearson's correlation and the chi-squared test. Techniques for linear algebra can be used for dimensionality reduction. Specifically, matrix factorization methods can be used to reduce a dataset into its constituent parts. Examples include the Eigen decomposition and the singular value decomposition methods. The parts can then be ranked, and a subset of those parts can be selected that best capture the salient structure of the matrix that can be used to best represent the dataset. The most common method of ranking these components is called principal component analysis, or PCA for short. Techniques for high dimensionality statistics can also be used for dimensionality reduction. These techniques are sometimes referred to as manifold learning and are used to create a low dimensionality projection of a high dimensionality data space, often for the purposes of data visualization. The projection is designed to both create a low dimensional representation of the dataset while best preserving the salient structure of the relationships in that data. Examples of manifolding learning techniques include the cone self-organizing map, Sampson's mapping, multidimensional scaling, and the t-distributed stochastic neighbor embedding. The features in the projection often have little relationship with the original columns, i.e., they don't have column names, which can be confusing to beginners. Next up are the AutoEncoder methods. Deep learning models can be constructed to perform dimensionality reduction. A popular approach is called AutoEncoders. This involves framing a supervised learning problem where a model must reproduce the input correctly. A neural network is then used that seeks out to compress the data flow of the bottleneck layer with far fewer dimensions than the original input data. The part of the model prior to and including the bottleneck is referred to the encoder, and the part of the model that reads the bottleneck output and then reconstructs the input is called the decoder. After the training, the decoder is discarded, and the output from the bottleneck is used directly as the reduced dimensionality of the input. Inputs transformed by this encoder can be fed into another model, not necessarily the same neural network model. The output of the encoder is a type of projection, and like projection methods, there is no direct relationship to the bottleneck output to the original input variables, making them challenging to interpret. Linear discriminant analysis, or LDA, is a linear machine learning algorithm used in multi-class classification. Linear discriminant analysis seeks to separate or discriminate the samples in the training dataset by class value. Specifically, the model seeks to find a linear combination of input variables that achieves the maximum separation of the sample classes and the minimum separation of the samples within each class. There are many ways to frame and solve an LDA. For example, it's common to describe the LDA model in terms of a Bayes theorem and conditional probabilities. In practice, LDA for multi-class classification is typically implemented using the tools for linear algebra and like PCA, uses matrix factorization at the core of its technique. Therefore, it's a good practice to standardize the data prior to fitting an LDA model. Alright, now that we're familiar with LDA at a high level, let's see how it can be used with the scikit-learn library. We can use LDA to calculate a projection of a dataset and then select a number of dimensions or components of the projection to use as inputs to the model. The scikit-learn library provides a linear discriminant analysis class that can be fit on the dataset and used to transform the training dataset and any additional dataset in the future. A snippet of that code is shown on screen. The output of LDA can be used as input to train a model. Perhaps the best approach is to create a pipeline where the first step is the LDA transform, and the next step is the learning model that takes the transform data to be inputted. Again, another snippet is shown on screen. It can also be a good idea to standardize data prior to performing the LDA transform if the input variables have different units or scales. Again, a code snippet for that is shown on screen. Alright, now that we're familiar with LDA and the LDA API, let's work through an example. Alright, let's work through an example of LDA. First, we're going to use the make classification function to create a contrived dataset with 10 class classification problems with 1,000 examples and 20 input features. We're also going to have 15 inputs of which are meaningful. The complete code is listed on screen. When we execute it, we get a dataset and the summarization of the shape input and output components. Next, we're going to use dimensionality reduction on the dataset while fitting a naive Bayes model. We're going to create a pipeline where the first step performs the LDA transform and selects 5 of the most important dimensions or components, then fits the naive Bayes model on these features. We don't need to standardize the variables on this dataset. All variables have the same scale by design. The pipeline is going to be evaluated using the repeated stratified cross-validation with 3 repeats and 10 folds per repeat. Performance is presented as the mean classification accuracy. The complete example is listed on screen. When we execute the code, it evaluates the model and reports the classification accuracy. In this example, you can see that the LDA transform with the naive Bayes achieves a performance of 31.4%. How do we know that reducing 20 dimensions of input down to 5 is good, or even the best we can do? The answer is we don't. 5 was an arbitrary choice. A better approach is to evaluate the same transforming model with different numbers of input features and then choose the number of features, the amount of dimensionality reduction, that results in the best average performance. LDA is limited in the number of components used in the dimensionality reduction to between the number of classes minus 1, in this case 10 minus 1 or 9. The example on screen performs this experiment and then summarizes the mean classification accuracy for each configuration. Running an example first reports the classification accuracy for each number of components and features selected. You can see a general trend of increased performance as the number of dimensions is increased. On this dataset, the results suggest a trade-off in the number of dimensions versus the classification accuracy of the model. Our results suggest that the default of 9 components achieves the best performance on the dataset, although with a general trade-off in fewer dimensions used. We're also going to create a box and whiskers plot for the distribution accuracy of scores for each configured number of dimensions. Again, you can see the trend of increasing classification accuracy with the number of components, with a limit at 9. You may choose to use an LDA transform and a naive Bayes model combination as our final model. This involves fitting the pipeline on all the available data, and then using the pipeline to make predictions on the new data. Importantly, the same transform must be performed on this new data, which is handled automatically via the pipeline. The code on screen is an example of fitting and using the final model with LDA. Running the code first fits the pipeline on all the available data, and then makes predictions on the new data. Here, the transform uses 9 of the most important components for the LDA transform, as we found from testing recently. A new row of data with 20 columns is provided, and it's automatically transformed to 9 components and then fed to the naive Bayes model in order to predict the class label. Reducing the number of input variables for predictive modeling is referred to as dimensionality reduction. Fewer input variables can result in a simpler predictive model that may have better performance when making predictions on new data. Perhaps the most popular technique for dimensionality reduction in machine learning is called PCA, which stands for Principal Component Analysis. This is an approach that comes from the field of linear algebra and can be used as a data preparation technique to create a projection of the dataset prior to fitting the model. PCA might be the most popular technique for dimensionality reduction. It can be thought of as a projection method where the data with m columns, features, is projected into a subspace with m or fewer columns, while retaining the essence of the original data. The PCA method can be described and implemented using tools of linear algebra, specifically a matrix decomposition like an agent decomposition or a single value decomposition. All right, so now we have this high-level look at PCA for dimensionality reduction. Let's see how we can use it using the scikit-learn library. We can use PCA to calculate a projection of the dataset and select a number of dimensions or principal components of the projection to be used as input to the model. The scikit-learn library provides a PCA class that can be used to fit a dataset and used to transform a training dataset and any additional dataset in the future. A snippet of code for this is shown on screen. The outputs of a PCA can then be used as input to train the model. Perhaps the best approach is to use a pipeline, where the first step in the PCA transform and the next step can be the learning algorithm that takes the transformed data as input. Again, a snippet for this is shown on screen. It can also be a good idea to normalize your data prior to performing PCA if the input variables have different units or scales. Again, a snippet of code for this is shown on screen. All right, now let's work through an example. Like we've seen a few times in this course, we're going to use the make classification function to create a contrived binary classification problem with 1,000 examples and 20 input features. 15 inputs are going to be meaningful. That code is listed on screen. Running an example creates the dataset and summarizes the shape of the input and output. Next, we can use dimensionality reduction on this dataset while fitting a logistic regression model. We're going to use a pipeline where the first step performs the PCA transform and then selects 10 of the most important dimensions or components, then fits a logistic regression model on the features. We don't need to normalize the variables in the dataset, as all the variables have been scaled by design. The pipeline will be evaluated using the repeated stratifold cross-validation with 3 repeats and 10 folds per repeat. Performance is presented as mean classification accuracy, and the complete example is shown on screen. Running the example first evaluates the model and then reports the classification accuracy. In this example, you can see that the PCA transform with logistic regression achieves a performance of about 81%. All right, well, how do we know that reducing 20 dimensions or the input down to 10 is good or the best we can do? Again, we don't, because 10 was an arbitrary choice. A better approach is to evaluate the same transform and model with different numbers of input features, and then choose the number of features, the amount of dimensionality reduction, that results in the best average performance. The example for this is shown on screen and summarizes the mean classification accuracy for each configuration. When we execute the code, it first reports the classification accuracy for each number of components and features selected. You can see there's a general trend of increased performance as the number of dimensions is increased. On this dataset, the results suggest a trade-off in the number of dimensions versus the classification accuracy of the model. What's interesting is we don't see any improvements beyond 15 components. This matches our definition of the problem, where only the first 15 components contain information about the class, and the remaining 5 are redundant. Again, we've created a box and whiskers plot to show the distribution of the accuracy scores for each configured number of dimensions. We can see a trend of increasing classification accuracy with the number of components, with the limit up to 15.